working in a coal mine, going down, 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 working in a coal mine, about to step down, working in a coal mine, going down, 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 working in a coal mine, about to step down.
Okay, so we've got enough kind of terms and concepts under our belt. We don't want to move forward until we've actually tried this stuff out and look at these results. So let's jump in and start some homework problems, and I'm going to work 10.2 and 10.4. Show you how to set it up in Excel. We might need to put the regression package data analysis add-in first, so I'll show you how to do that, and then we'll run these problems. And you'll actually, I think you'll be pleased when you discover how easy it is to run regressions in Excel. The complex part is interpreting the result, and that's what we'll focus on. Okay, so we're on problem 10.2 now, and we're going to run a regression here, but we're going to do everything. We're going to do more than just a regression. We're going to do the scatter plot and calculate the correlation kind of by hand, so to speak, so we can see how this all works together. Now, first off, though, however, you need to have a add-in in your Excel to do regressions. So if you don't have that already, let me just quickly show you how to do that. What do you want to go to File and Options, and you want to go onto this add-ins option right here, and down at the bottom here, Manage Excel Add-ins, hit Go. Now it's going to give me the screwy error message, but what you'll get is this little window right here, and you want to select that analysis tool pack. You hit OK, and then it'll install the analysis tool pack. Okay, once that's done, I've already done it, so I can just close this. You go up to Data, and you'll have Data Analysis over here, from which we can select Run Regression, which we'll do here in just a moment. Okay, but however, first, let's read what the problem says and work step by step. It says this file contains midterm and final exam scores for 96 students in a corporate finance course. Each row contains the 2 exam scores for a given student, so you might expect them to be positively correlated. A, create a scatter plot of the final exam score, and that's going to be the vertical, the y-axis, and versus the midterm score, that's our x. Alright, so let's do that. I'm going to select that range, including the labels at the top. I'm going to insert, scatter plot. Okay, there's my scatter plot. Now, I'm not going to worry about editing this too much because we can see it's tightly linear. It's very positively correlated. So it looks like the midterm score is a good predictor of the final score. And by the way, let's make sure that it's putting the midterm on the x-axis and the final on the y-axis. So let me just select data here and then hit Final, hit Edit, and see the x values are the b's, which are the midterms. The y values are the c's, which is the final. So that's correct. And you know what? I'll go ahead and truncate the axes range so we can kind of zoom in a little bit. I'm going to put the minimum at 60 on that one, and I think on this one I'll put it at 50 for the finals. Okay, so we can see that that's quite linear, and we might also just make it look nice and know what's going on here. Label these midterm scores, and this one would be final scores. Okay, then I actually don't need a... Okay, so a nice scatter plot showing a nice positively correlated linear relationship. So far, so good. And it says, based on the visual evidence, would you say that the scores for the 2 exams are strongly related? Yes. They move quite nicely together, and it's a positive linear relationship. Okay, so there's part A. Let's kind of just set this down here. B, superimpose a trend line on the scatter plot. We know how to do that. Select the scatter plot, select this little plus sign, and select trend line, and then let's go to the trend line options, and we want it to show, it's over here in trend line options, we want it to show the equation, and let's go ahead and have it display the R square as well. And let's move this a little bit. Let me format this so we can read it. I like to make it a different color, blow it up a little bit, and that's our regression equation, along with our R square, which remember is the measurement of how well that regression equation explains the variances in y based on the variances in x. Okay, what does this equation indicate in terms of predicting a student's final exam score from his or her midterm score? Let's spell that out. B. Well, so we've got, actually, I'm just going to pencil this in, make it a little faster. We've got y equals, let's round this point. It's almost 1 x plus 0.9, 0.99 x plus 0.9. What this means is that for each 1 point increase in x, your final exam score is predicted to go up by 0.99. It's almost 1 to 1. So plus 1 if your midterm is +1, your final is going to be +1. And that's pretty much what we have here. You'll notice that that's almost a 45-degree line there. It's got a pretty low intercept as well. So there's kind of a 45-degree relationship here between midterm scores and final scores. The midterm scores up a point, final scores up. Okay, so the midterm score is a very good predictor of the final score. And we might write this down in this fashion. For each 1 point increase in midterm score, the final score is predicted to increase by 0.99. Very strong relationship. C, run a regression to confirm the trend line equation from part B. Now, let me show you how to do a regression. It's devilishly easy with that Excel add-on. We want to go up to data, over here to data analysis, and then we'll select regression. Now it just allows you to select the ranges for our y's and x's and a few other options. I already actually did this once when I was warming up, but I'll reset everything. Okay, so our input y range, that's going to be the final scores. So I'm just going to select that range now, all the scores. Our input x range is going to be the midterm score, so I'm going to select that range. You can click and drag, you can type in whatever you want. Okay, I'm going to go ahead and go actually from C1 to 97 and B1 to 97, and then I'm going to tell Excel that I've also selected my labels, because at the very top here I'm using the labels. Whoops, confidence level 95%, that's the default. Okay, then where's it going to display our output? Well, let's just select a cell over here. Let's just click on that and select a cell, and then it'll put a table of regression results over here starting in that cell. And that's all we'll do for now. Maybe in the next exercise or two we'll add a few more things in terms of looking at residuals and plots and whatnot, but this will be good enough for now, so I can hit OK. There's my regression, and let's see what we got here. Y equals 0.997x. That's my coefficient on midterm, as you can see right here in coefficient. Okay, we'll worry about all the other regression results later once we kind of have talked about them. Our R square, there's our R square, 0.5795, 0.5795. That agrees with the trend line. Multiple R would of course be the square. And by the way, I want to do this. I want to run the correlation. Just manually calculate the correlation. Correl between B2, B97 and C2 to C97. So correlation is 0.76. Well, note that's the same as the multiple R. That's the square root of the R squared. The R square is the correlation square, so we can calculate R squared manually too by just multiplying that correlation by itself, squaring the correlation. Okay, so R squared 5795, that's the same as here. That's the same as here. Correlation, that's the multiple R. Okay, we could take the square root of that and get the multiple R. And then our coefficient on the only x variable here, which is midterm, right down here where it says coefficient. Okay, so I'll highlight the things actually that we're looking at so far. We're looking at the coefficient on midterm. We do have the intercept here in our regression equation, 0.9079. There it is right there. So I'll highlight that too. We've got the multiple R and the R square. Okay, now we've got a lot more things, of course, in the regression output, and that helps us to interpret how useful this regression is. And one thing we've talked about already is the standard error. It's 6.22. So what that's telling us is that the predicted Y values are mostly within about 6 points of the actual Y values. In other words, the trend line is within typically about 6 points of the actual scores, 2/3 of the time roughly. Okay, but now there's a few other things in this output here that indicates the strength of this regression, particularly with respect to the coefficients on the midterm. And that's something we'll come back to later, looking at the t-stat and the p-value. I'll just tell you right now that that's a very high t-stat and that's an extremely low p-value. It's practically 0. So that means that our midterm coefficient is very significant. I'll highlight that like that. So we've got a very good result here. Very solid regression. So this is really data we can run with. A pretty decent R square. That's not the highest R square, but anything above 0.5 is typically pretty powerful. But we've got really good values down here on our coefficient. So that's a very nice result. Okay, let's move on to problem 10.4. It says, It's page 486. The owner of original Italian pizza restaurant chain wants to understand which variable most strongly influences the sales of his specialty deep dish pizza. He has gathered data on the monthly sales of deep dish pizzas at his restaurants and observations on other potentially relevant variables for each of his 15 outlets in Indiana. These data are provided in the file. Estimate a simple linear regression equation between the quantity sold y and each of the following candidates for the best explanatory variable. And I'm going to highlight the ones it wants us to estimate. Average price, monthly advertising, disposable income. Okay, actually, we're only going to estimate regressions with these three that are given. Let's highlight those. Those are going to be our right hand or explanatory or independent variables. And of course, quantity sold here is going to be our, left hand or dependent variable. Okay, so now we're just running regressions, one at a time on each of the right-hand variables. Pretty simple procedure, data analysis, regression, okay. And my Y input range is going to be quantity sold. Whoops, I need to click here and then select quantity sold range. Okay, my X, first off, is going to be average price. And I am selecting the labels. Typical 95% confidence level, we won't change that. My output range, let's put these, let's just put them over here to the right, I guess. And we'll just stick with this for now. So bam, it instantly calculates the regression. That's some amazing computing power. And what are we interested in? Well, we're interested in R square. I'm going to highlight what we care about. We care about R square. The standard error. Standard error looks pretty big. It's 12,800 on sales, so there's something around 40, 60, 80,000. That's a pretty big standard error, and that's a pathetically small R square. And then of course the coefficient on what we're regressing, which is average price coefficient. And by the way, this has a high p-value, so it's not even significant. We'll talk about that here pretty soon. Okay, and you know what, because we're only talking about R square, standard error, and coefficients, let's just delete this junk for now. Okay, and let's run our next regression. Data, analysis, regression, okay. My input range is going to be the same for each of these, my Y's. I'm only going to change my X's, and actually the easiest way to do it would probably be just to type in the D's now. So this is our regression on monthly advertising expenditures. We're sticking the labels in here. Notice when you have the labels in there, it labels your coefficients automatically, so that's kind of convenient. And we'll put the output range right here in H1. Okay, bada boom, there's our regression. Monthly advertising expenditures. What are we interested in? Let's do this. Let's format this up a little bit. Put a border on that. Okay, what are we interested in? R square. Use a different color here. How about blue? Standard error. Okay, R square is a lot higher. Nice. Standard error is a lot smaller. So far, so good. I'm liking that. And then our coefficient on advertising expenditures, 1.75. Okay, so what does that mean? It's R square is closer to 1. We like that. That means this is explaining about 87% of the variation in Y. This is the single X variable. The variance in it is explaining the variance in sales. The standard error means that the estimated line is typically within about 4,800 of the actual Y. So that's good. It's a lot better than it was here. And then the coefficient means that for every 1 unit increase in monthly advertising expenditures, for every dollar increase, because that's measured in dollars, right? For every dollar increase in monthly advertising expenditures, we get a $1.75 increase in sales. So that's music to our ears, right? If we're profit-oriented business owners, you spend $1, you get $1.75 in return. That sounds like a good investment, right? So you can see that this is information worth knowing. We're already getting very good results from the regression. We've only begun to talk about interpreting these results. We've got a small p-value and a huge t-stat. Those we'll talk about later, but those are good, really good signs. So I'm liking the blues here. I'm liking monthly advertising expenditures. I think that's going to be my winner. But just in case, let's run our final regression, regressing quantity sold on disposable income per household. And same procedure, data, analysis, regression. Okay. Input range is still B's. The Y range, the X is now E's, which is the disposable income column. And then I'll put my output range up here in J1. And then we can compare this side by side. And let's see what we get here for our R squared. That's pretty small. Anything less than 0.5 is pretty much no good. Our standard error is almost as big as it was in when we regress on average price, so that's no good. So the coefficient, such as it is, okay, it says for every $1 increase in disposable income per household, we get a $2.94 increase in sales. But as we've talked about, these the R square and the standard error don't give much credence to this output, and the p-value is a little on the high side. It's above 5%, and the t-stats okay. The p-value's pretty close, but I'm just not liking that R square. So for that reason, I don't like the disposable income as an explanatory variable nearly as much as I like advertising expenditures. So of the 3 regressions we ran, the advertising expenditures by far is the best one. Okay, this one's good, these ones, and not so much. Okay, so I'm just going to ink on here my responses. So far, so good, right? Let's ratchet things up a little bit and make it more complicated. Okay, so it's up to you to run to do problem 10 by yourself. But it's a very straightforward question, and it's going to be the exact same procedure we just used in 10.2 and 10.4, so it should be pretty easy for you. Okay, moving on. Now we've done simple regression, which is where we only have one x variable, one right-hand variable, and we can do a lot with that, as we just saw, but we can do so much more if we throw more right-hand explanatory variables into the mix. And when we do that, that's called multiple regression. Now, it's a lot more complex mathematically, but the good news for us is that Excel does all that for us, and interpreting the results is pretty much exactly the same as with simple regression. So we're not going to have to talk too much about multiple regression before we can launch in and actually start running some multiple regressions. Okay, like I said, we have multiple x's, multiple right-hand explanatory variables. The difference is this: the coefficient for each x will represent the expected change in the estimated y when that x increases by 1 unit and all the other x's are held constant. So you sometimes hear this referred to as we're controlling for the values of all the other x's and kind of taking each right-hand variable individually and saying what's its effect on y when only it changes. Okay, controlling for the other x's, holding the other x's constant. Okay, and that's all I really want to say about it before we do it. So let's jump in, and now we're going to do example 10.2. Okay, so I've loaded the data into Excel here, and it says, I'm on page 489, example 10.2, explaining overhead costs at Bendrix. If you've been following along in the chapter, they've been using this as one of their major examples. Okay, and it says, estimate and interpret the equation for overhead when both explanatory variables, machine hours and production runs, are included in the regression equation. Show you how easy this is. You should be used to this by now. Data analysis regression. Okay. My input range is the this time it's the D. What we're trying to explain here is the overhead costs. So I'm going to select the overhead, column D. And my input X range now, and the only difference I'm doing now is I'm going to select 2 X's, columns B and C. One is machine hours, one is production runs. Okay, so this is a manufacturing company, and they're trying to say how much effect does the number of machine hours that they run have on overhead? How much effect does the number of production runs they do have on overhead? Okay, so I've got selected the right ranges for the variables here. I have labels. We'll do 95% confidence interval. That's standard. We'll never change that. Let me select my output range. I'll put my output way up here. So I'll select F2. Okay, and that's enough for now. Oops. Oh, I screwed up my input range here. Let me redo this. Input range is B and C. like that. Okay, my output range is F2. I think everything's correct now. There we go. Okay, you always want to double click to widen out these columns so they show you everything in the regression table. Okay, now what are we interested in? We're interested in our R-square. So let me pin this. I'm gonna highlight everything we're interested in. We're interested in our multiple R. Well, let's just stick with R-square, standard error, and then our coefficients on each variable of interest. Okay. Now, if you've got the book in your hand, I'm on page 490. You can see we've duplicated exactly what they got. They're using the Stat Tools add-in. We're using, which you have to pay for. I'm using Excel's data analysis tool pack, which is free. Okay, so what's going on here? Well, we've got R-square of 0.86, which is pretty high. So we know this has a pretty good amount of explanatory power. It's explaining about 87% of the variation. What we remember that is the variation in these two variables, each individually holding the other one constant, but including it, is explaining 87% of the variation in the left-hand variable of overhead. The standard error is $4,100. Okay, so overhead is money, and this is money as well. It's a Y. So what that tells us is that we're typically within about $4,100, the estimated Y to the actual Y. So that's pretty good. When we're talking values around 80, 90, 100,000 to get within 4,000, that's pretty good. So I'm thinking that those are both good results. And then the coefficients, and as long as our p-values and t-statistics are in the right range, which they are, and we'll talk about that here shortly, we're looking for large t-statistics and small p-values. And those p-values are definitely tiny, practically 0. And our t-stats are both large, well above 2. So we can put a lot of confidence in these coefficients. And what does this say? It says, holding production runs constant, a 1 unit increase in machine hours increases overhead by $43. And likewise for production runs, what this means is that holding machine hours constant, a 1 unit increase in production runs increases overhead by $883. In fact, because we're measuring our Y in dollars, we could actually label all of these as dollar values. That would be totally proper. Okay, so a multiple regression. Easy peasy lemon squeezy, right? Let's okay, so we can move on now. And we'll work one of the homework problems. Let's jump to 1016. Okay, 1016, page 492. A trucking company wants to predict the yearly maintenance expense, Y, for a truck using the number of miles driven during the year, that's our X1, and the age of the truck, that's our X2, at the beginning of the year. The company has gathered the data, here it is, where each observation corresponds to a particular truck. You can see those over here. This is kind of a... Alright, part A says estimate a multiple regression equation using the given data, and interpret each of the estimated regression coefficients. Data, analysis, regression, input Y range. We're trying to predict maintenance expense. That's what's being predicted. That's the left-hand variable. And the right-hand or X variables are miles driven and age of truck. Okay, we have labels. We want 95% confidence. We would put the output right here. And you know what? This time I'm going to show us a residual plot. I'm going to show us residuals and residual plot, just to do something different. Okay, and we'll look at those here in a bit. But let's start off by focusing on our regression output. Okay, so first off, what's our R-square? 0.95, really nice. Nice R-squared, I like that. Standard error is 66. Now, what do we say about that? We're talking about predicting expense, and it looks like the expense, you know, let me just do this. I'm going to calculate the mean of the expenses here, equals average of B2 to B25, B2 to B24, rather. $500 on average is the maintenance expense, and we're hitting it within $66. Hey, I'm liking that. That's great. We're typically getting that within $66. I think that's pretty solid. Okay, so I'm liking our R-square. I'm liking our standard error. Let's look at our intercepts. And again, because we're estimating something that's a dollar cost over here, we can go ahead and put these in dollars. Okay, so what does it say? It says miles driven is 0.07, 7 cents. It says for each 1 unit increase in mile driven, so for each extra mile driven, we've got a 7-cent increase in maintenance costs. So let me go ahead and write that down. So interpretation for each 1 unit increase in miles driven. Let me say this. We predict a 0.07 7-cent increase in maintenance cost. And then for age of truck, it's extra $10.71 for each 1 unit increase in the age of a truck, i.e. each year older. We're measuring that in years. We predict a $10.71 increase in maintenance cost. Why is the magnitude of the miles driven coefficient so much lower than the magnitude of the age of truck coefficient? Well, it's basically this. Older trucks are going to need more work. They're going to need more kind of heavy duty maintenance. They might need to have their engines overhauled or something like that. So the average expenses for older trucks are higher. But notice that miles driven, it's a typical semi driver, a good one will drive something like 100,000 miles in a year. It's a good, my uncle's a semi driver, and he says you make 500 miles a day on a good day, and let's say you work 300 days a year, 150,000 miles is pretty heavy. 150,000 miles is a pretty good workload for a year for a semi driver. So you're racking up those miles pretty quickly. Okay, so you're getting 150,000 times this each year. You're only getting 1 times this each year. And it says it's because miles driven is not as important in predicting maintenance expense. Well, no, I think I pretty much explained that. Miles driven is the big driver, and it accumulates on a smaller coefficient, but hundreds of thousands of times per year. Okay, and finally in part B it says, interpret the standard error of estimate SE and R squared for these data. Well, we did that already, didn't we? We said this explains 95%. The changes in these two variables, holding the other one constant, interprets 95% of the change in the Y variable, the dependent variable, maintenance expense. And the standard error, we said we're hitting that within about $66. The estimated value to the actual value, typically. Okay, now also we haven't talked about this yet, but let me go over here and mention that really probably the most important things in the regression output here. We're looking for high t-stats and small p-values. So we have a high t-stat and a small p-value almost 0 with miles driven, so that's highly significant. We actually don't have a very high t-stat, and we have a pretty huge p-value here with age of truck. So age of truck, we're actually, even though we've got a strong coefficient, it's not significant, so we're going to rule that out. And in the next little lecture bit, I'll explain how we interpret t-stat and p-value. It's actually very familiar from what we've done in the last unit. Okay, finally, let's look at the residual plot. We're going a little bit above and beyond, but I just wanted to show you some of the other output we can get from Excel. And what this is showing us is the residuals, right? The distance between the predicted Y and the actual Y for miles driven. And what we're looking for here is no particular pattern. So it's kind of all over the place. It's actually got a little bit of an upside down kind of parabola, but it's pretty spread out, and there's no strong pattern here. So what that tells us is that we're not dealing with any collinearity problems with this variable. And same thing with age of truck. It's kind of a similar pattern, but it's pretty spread out. Those are things once you get a little more advanced level of regression that you'll be really interested in. Okay, problem 11.2, page 545. The owner of the original Italian pizza restaurant chain would like to predict the sales of a specialty deep dish pizza. You'll notice this is a repeat of, I think, is it 10 point? Yeah, repeat of 10.4. Okay, so it's familiar data. We've already run some regressions. He has gathered data on the monthly sales, observations on other potentially relevant variables for each of the 15 outlets. Okay, all we're going to do now is a multiple regression. Well, that's easy. So over here we did 3 different individual simple regressions. Now we're going to do them all at once. This is actually very easy. Data analysis, regression. Okay. Now what's the Y variable? Y variable is quantity sold. Actually, I want to include that with the labels. Let me do that again. Quantity sold with the labels. And now, instead of doing this individually, we're going to select price, monthly advertising, disposable income all at once. We're going to show with labels. We're going to put the output over here. And okay. We got a nice R squared. Standard error is 3,300 on quantities of 60, 70, 80,000. I think that's pretty good. This here's good. This here's good. ANOVA, we've got a pretty high F ratio and a tiny p-value there, so that stuff's all good. Let's look at our p-values and our coefficients. Yeah, they're all minuscule. The largest one, well, 0.08 on their intercept, but that's irrelevant. So, yeah, we're looking good here. We've got low p-values there. Low p-values. Pretty significant high t-stats. Now, of course, we see this average price works in the negative direction. Let's put this in dollars. And we're saying for each 1 unit increase in price, so for each $1 increase in price, we expect a location to have $4,000 fewer sales in a not monthly. This is monthly. So yeah, $4,000 less per month for 1 unit increase in price. That makes perfect sense. It's got a high t-stat. It's close to -4. Absolute value's high. It's got a low p-value, so I'm liking that. And monthly advertising expenditures, they pay off. For every $1 extra advertising, we get $1.45 extra sales. I'm loving that. And then for every $1 increase in average disposable household income, we get an extra $1.53 in sales. So I'm liking that. Low p-values, high t-stats, coefficients make sense. So I think we're all good here. It says in B, is there any evidence of any violations of the key assumptions of regression analysis? Okay, actually, to answer the answer part B, is there any evidence of violations of the key assumptions, I forgot to do something we should have done, so I'm going to run this regression again. This time I want residuals, the residual plot. And yeah, we'll go ahead and overwrite what we already had. Let me highlight again our R squared. Remember, our R squared was good. Our standard error was pretty good. I'm highlighting all of this. All of our p-values were essentially 0. Those are all good. And that means these coefficients with our high t-stats and these coefficients I'm converting to dollars, and they're all good. Okay, and then my plot of residuals. My plots of residuals here, doesn't look like there's any linear patterns in here, so we don't have collinearity problems. Okay, these are all just kind of lumps. So that checks out, and that's basically all for right now. That's all we need to do in terms of assessing whether we're meeting our regression assumptions. So that's all. That stuff all checks out. That stuff's good. Okay, so that's part B, and then part C says which of the variables in this equation have regression coefficients that are statistically different from 0 at the 5% significance level. All of them. All right. It's basically asking which ones have p-values less than 0.05. All of them. Okay, so they're all significant. They're all good. And then part D, given your findings in C, which variables, if any, would you choose to remove from the equation? None. Why? Because they're all strongly significant with very low p-values and very high t-stats. Okay, and that's what it's all about. Remember, it's about the R square, getting that as close to 1 as possible, having a smaller standard error. By the way, let's see if our standard error is less. Oh yeah, standard error is lower here than it was in any, and our best regression here was monthly advertising, and there our standard error was 4,800, and over here our standard error is 3,300. So that's good. Okay, all of our t-stats and p-values check out. It's about having low p-values, high t-stats, R square closer to 1 is better, and lower standard error. Those are the four main things that we should be looking at when we interpret the regression, and then we can interpret the coefficients just like we did. We said for every $1 increase in the price, that store sees $4,000 fewer sales per month. For every $1 increase in advertising expenditures, that store sees $1.45 increase in sales per month. For every $1 increase in disposable income, that store sees $1.53 increase in sales. Okay, one more for old time's sake, and this is 11.4. The trucking company wants to predict the yearly maintenance expense for a truck using the number of miles driven and the age of the truck. Hey, we've done this already too, haven't we? I like these problems that line up with each other. That's let's see, that's 10.16. Yeah. So we're repeating the data in 10.16, and all we're going to do is a multiple regression instead of a single one. Estimate a multiple regression using the given data. So this will be pretty easy and pretty fast regression. Y's are the maintenance expense, and the X's are miles and age. Alrighty, we've got labels. Let's put our output range right here, and let's do all of that. Let's widen these bad boys out. Okay, so kind of formatted everything up. You can see those residual plots, no strong patterns. Okay, this goes down, but then it goes up, so there's no overall pattern. Same thing with this. So we're probably doing pretty good on our regression assumptions. Now let's look at our key outputs. Actually, let's go back to the problem here. It says, does autocorrelation appear to be a problem? What about multicollinearity? What about heteroscedasticity? Okay, so to assess, I'm going to work backwards on B. To assess heteroscedasticity, we just want to look and see if the variability in Y is consistent across all of the X's, and the best way to do that is just to look at scatter plots. So let's start off with maintenance expense miles driven, and let's just insert a scatter plot. Actually, let's just insert a scatter plot like this, and we'll stick them down here. I actually want to have the X values as the miles driven, so I want to change the X values to C's, and I want to have the maintenance expense, the B's, be my Y variable. Okay, so once I do that, does it seem like the Y's are more spread out at lower values of X versus higher values of X? No, it sure doesn't. And let's do that for also maintenance expense versus age of truck. Let's make a scatter plot for those. And let me again flip the axes here. I want X to be the D, the age of truck values. So I'm going to put D values in the X, and then my Y values, I want that to be the B, the expense. So as soon as I just flip that around, okay, and let's drag this down here as well. Just kind of get it out of the way. And this one we'll call maintenance expense versus truck age. And does it look like the Y's are more spread out down here than up here? Not particularly. Okay, so heteroscedasticity, no. And actually we can label, we can write our responses somewhere. Let's do that up here. B, no evidence of heteroscedasticity from X, Y scatter plots. In other words, Y shows similar variability for all values of X. Okay, let's talk about autocorrelation. And I didn't talk about this before, but I'll mention it now. Autocorrelation is usually only a problem. That means that a data series is correlated with itself. And it's usually only a problem for time series data. So if we're not looking at time series data, we can pretty much rule out autocorrelation. So I'll just say no. This is cross-sectional, not time series data. No reason to suspect auto correlation. Okay, finally, multicollinearity, and that refers to whether these two x variables are correlated with each other. The way to test that is to create a correlation table, and we actually did this way back, I think, in homework 1. So I'm going to create a little correlation table here: maintenance expense, miles, age, maintenance expense, maintenance cost, miles, age. Okay, remember how to do this. This is going to be the correlation between maintenance expense and maintenance expense, and of course that's going to equal 1. Okay, the correlation between maintenance expense and miles equals, and now actually what I can do is if I lock these cell references and then slide it over, yeah, I should only slide the second one and then the third one. Okay, so I've got my correlation between maintenance and maintenance, it's 1. Between maintenance and miles, it's 0.973. Between maintenance and age is 0.885. Okay, between miles and miles, of course, that's a correlation of this with itself, so we'll enter that in for both arrays. And then I will lock the first array, drag it over. Now we can get the correlation between miles and age. And of course, correlation between age and age, I could type a 1 in there, but just to be proper, I will enter that as a formula. And it's 1, of course. Okay, let's put a little more space so we can isolate this. Now, what we're seeing here is that we've got a high correlation between miles and maintenance expense, as we suspect, and age and maintenance expense. But look, we also have a pretty high correlation between age and miles. So what that tells us is that we have multicollinearity. These variables here, miles and age, themselves correlate strongly with each other. So what that tells us is kind of that our regression model is what we might say overspecified. These things both, because they're correlated with each other, move in the same direction, so they kind of both impact the regression result in exactly the same way. So it might be better to do the regression on one of them at a time, and we might think about getting rid of one of them because of that multicollinearity issue. Now, okay, part C then says find 95% confidence intervals for the regression coefficients on the two x's. Right? That's given in our output here. I highlighted it. The lower 95%, the upper 95%. And what we see that is for miles driven, the p-values are small only on miles driven. And then we have a range between 0.05 and 0.09. Okay, so that's significant, and then we've got a nice, that's significant, and then we've got a nice interval there. That makes perfect sense. Age of truck is both not significant, and notice that its confidence interval spans 0. It goes from -8 to 29. So we can't even kind of bound that at a range that doesn't include 0. So that leads us to think, primarily because the p-value is too high, but also because this range crosses 0. We might say, you know what, age of truck isn't helping us much, and because we have the multicollinearity between these two based on that correlation, we might say let's run this regression again without age of truck. Let's run it on just miles. So I'm going to go ahead and do that. The problem doesn't ask to do this, but it's so easy we might as well. Okay, so now the input range is just going to be C for the x's through 24. That's correct. And let's put that output over here. And let's just do a little side-by-side comparison. In terms of our R square, we go from 95 when we had both variables to 94.7. Wow, it's almost exactly the same. That's good. Standard error, 66.2, 66.8, almost exactly the same. We're passing our F ratio test, ANOVA, that's all good. We actually get a little bit better confidence interval on miles driven. The p-value is still extremely small. In fact, it's even smaller than it was last time. Last time it was 10 to the negative 8th power. Now it's to the negative 15th. And the t-stat's large. It's even larger than it was last time. And the coefficient is a little bit larger. So in the name of having a parsimonious model, as simple as possible, as spare as possible, I'm going to say this one here is the better regression. Okay? Even though it only uses one variable. That's the most important variable. That's the relevant variable. The age of truck variable doesn't really do anything for us. So that just demonstrates that it's perfectly good, perfectly legitimate to run a regression with a smaller number of explanatory variables in many cases. Okay, so that covers the walkthroughs. You got 11.5 to do on your own. Don't sweat it. Excel's going to do all the work for you as long as you know how to read that. As long as you know how to read that output table, you will be in very good shape.